Good morning. Happy Thursday. Welcome to the end of our third week here in our 9-week radio Zoom term schedule. It feels like it can't really be the end of week three, but yeah, we're flying through our material. We're sitting at a great spot. I'm excited to be able to move through, have a whole unit behind us, 6 lessons even. Yesterday, we started with lesson 7, and I should have prefaced it with there's a lot of information in lesson 7 that usually takes me 3 classes to go through. But with the way I've been tailing on the end of every lesson before starting a new lesson, we'll see how it goes. I'm hopeful that I can wrap up lesson 7 today so you can go into the weekend with 2 lessons of Unit 2 under your belt, and we'll start fresh with Lesson 8 on Monday. If you're just tuning in, my name is Kobe Flatt, and for the next hour, we're going to be going through the MAP4C Foundations for College Mathematics course. Every Monday to Thursday, we go through course curriculum content. As I said, we are at the end of week 3. Today is our last day of broadcasting for the week because Fridays we don't ever schedule radio classes, as it's a chance for you to get caught up on any outstanding work. Fridays you should be finishing work, hopefully sending in lessons at the end of the day. If not, please send them in by Mondays. Remember that extra added bonus incentive to be submitting lessons. Not only are you working towards obtaining the credit, going to the overall probably goal for most of you to get your diploma, by submitting lessons, you also get your name entered into a draw. Now, every term, at the end of every term, we do a draw. Sometimes it's prizes, sometimes it's a check for $100. If you are submitting lessons, your name gets entered into one draw. After submitting all 20 lessons, completing your final assessment, and you get the credit, everyone who has obtained a credit gets their name entered into a second draw. So some added bonus incentive there to be using your Fridays wisely, getting caught up on work, submitting that work so that your name can be entered into our draw. Yesterday we looked at quadratic. We wanted to look specifically at linear functions. Today we're getting into quadratic functions. We have these mathematical models that we talked about that allow us to represent the relationship between real-world quantities, analyze current behavior, predict future behavior, different ways that can be represented. You can represent data through numerical values by looking at tables, graphical values, seeing it in graph form, or algebraic, which comes across and through as equations. If you want to go back and refresh your memory, remember all of our classes are recorded. The quick synopsis that I'm going to give is yesterday we looked at linear models. We could tell if a model was linear if, when presented with a table of values, the first differences were equal. If you were presented with a graph, you could see the straight line. A straight line represents a linear model. If the equation of the line can be written in the form y equals mx plus b, then you have a linear model. You can also tell if a model is linear if the rate of change is constant. We did some practices together looking at those different models. We learned first differences in a table of values. We saw linear on a graph. We practiced putting the equation into y equals mx plus b. We ended off with some graphing. We learned how to plot coordinates, also called Cartesian coordinates, on a graph by locating a point on the coordinate plane. We did not get to the point of intersection yesterday, which is where I want to start today's lesson before we jump into part 2 of lesson 7. When we're talking point of intersection, we are talking the point on the graph on our Cartesian plane where two lines meet, where they cross, where they intersect. That is our point of intersection. On the board in front of me, if you're following along on Zoom, I have a graph with two lines. Our red line is y equals 2x plus 1, and our blue line is y equals x plus 2. The two lines cross and they meet at our point of intersection, which is 1 and 3. Yesterday when we talked about coordinate pairs, we said how you always, in a coordinate pair, list the x-axis first, then the y. You can remember it alphabetical order. X comes before y. We have to have x first. So we know that 1 and 3 means we're looking at the 1 on our x-axis. And remember, our x-axis is our horizontal axis. Y is the vertical axis. So we're going along the horizontal plane, stopping at 1, going up the vertical plane, our y-axis at 3, and that is where our lines intersect. That is the point of intersection. I want to practice doing one together so that we can really understand what it is that we're looking for. This is the last practice question from part 1 of lesson 7 that sums up everything we did nicely together, where we put our knowledge of finding slope and y-intercept together. We wanted to be able to read the equation. So here we have, I'm going to change colors. We have y equals 2x plus 3. If we put it, y equals mx plus b, we can see our m is 2, which means 2 over 1, our rise over run, and our b is our y-intercept, and that's positive 3. So our blue line, our y-intercept is at positive 3. That's where we're going to put our first coordinate plot, our pair, at 0 and 3. Then the rise over run tells me I'm going up 2 and over 1. So my next coordinate pair is going to be at 1 and 5. Then I'm going up 2 and over 1, so I'm at 3 and 7. Up 2 over 1, I'm at 4 and 9. So what I can do is I can extrapolate, I can use a line of best fit, and I do have a meter stick here. I don't know if I should use it on the smartboard though. So very carefully I'm going to try to make a straight line myself. It's just like playing connect the dots, and you're going to make a straight line. Please always use a ruler. I am not using a ruler because I don't know if I should on this board. My next equation is y equals x plus 9. If it's just an x, there's this imaginary 1. So my m is 1, my slope is 1 over 1, my b-intercept is 9. So here I would have 9 is my first, and then I'm going up 1, over 1, up 1, over 1, up 1, over 1, over 1, up 1, over 1, up 1, and then you would see my green line would intersect. Now this was not a great one to choose as an example because I'm way off my grid, but you can see where they intersect is my point of intersection. I should have started with a lower y-intercept for the sake of this problem so that you could better see. So what if just for funsies so that I can illustrate this a little bit better, I'm going to change my green line and my point of intersection to get a new point of intersection. So we're going to pretend, I'm going to cross out this one, and I'm going to say my second equation is y equals, I could even make it negative, let's make it negative 2 over 1x plus, and I could do 5. Alright, we're going to pretend it's that, and hopefully I'll get a better. So my slope is negative 2 over 1, and my b-intercept is positive 5. So now if I have it at 5, and I'm going to go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Eventually, this still wasn't the best, because my lines are so close together, it's going to take a long time for them to cross, and again I'm off the graph. Alright, one more time, team. One more time, we're going to say that, oh, you know what, that was my fault, because it's positive 1, not negative 1. I'm not going to the left. This can still work. Here we go. Down 2 over, whoops, I'm going to go back to green. I'm going down 2 over 1, down 2 over 1. There we go. Silly Kobe. Now we have this point of intersection, because it's not a negative 1, it's a negative 2. I'm going down 2, but I'm still going to the right, positive 1. So now we have a point of intersection. Here we are. We can see, and it would obviously be better if I had used a ruler, but we can see our point of intersection where they meet is at, always do x first, so here we're looking at a 0.5 if I'm semi-accurate, and on my y-axis is 4. So I'm at 0.5 and 4. That's better. I'm going to fix this on my slides for next time. I'm not sure why I didn't catch that last time, but now for future reference we'll have a better example to use for finding a point of intersection. Alright, that brings us to the end of Lesson 7, Part 1. But you can see that Lesson 7 talks about linear, quadratic, and exponential functions. We've gone over linear. We are going to try now to squeeze in both quadratic and exponential functions here. So we're going to skip this because we did that. We're going to continue looking at quadratic and exponential functions to better understand how to graph and use. Our learning goals for this half of the lesson are to be able to understand how to graph the y-intercept form of the line. We'll be able to understand the meaning of a, h, and k in the equation y equals a. In our brackets we have x minus h, close your bracket, squared plus k. And we'll be able to substitute into quadratic equations as well as then plot and graph them. So what is a quadratic equation? This is on page 11 of your IL booklet. We are looking specifically now at quadratic functions. In situations that do not involve constant rates of change, we must use a non-linear model. Quadratic models have the following characteristics. In a table of values, the second differences are equal and non-zero. We know that in linear models, the first differences are equal. In quadratic models, the second differences are equal and can't equal 0. In a quadratic model, if you see a graph that has a curve, which is called a parabola, we can tell that it is quadratic, as opposed to the straight line, which is linear. In a linear model, we used y equals mx plus b. In a quadratic model, the equation can be written in the form y equals ax squared plus bx plus c, as long as a does not equal 0. So let's try what that means to find second differences. We know how to find first differences. We know that when we are trying to find first differences, we're just taking the difference between the first set. Here we want to take the difference between the second set. Oh, also team, I just found my notes on our point of intersection, and I see I wanted to go into further detail. Do we go back and go into further detail? You know what? I'm going to. I'm going to back it up so that you have a better understanding, because I feel like I did just kind of rush through that. So here. And now I remember my line of thinking. Now that I'm looking at my notes, I know what I was thinking now. So here we go. We're going to just pause, time out, go back. Let's look at point of intersection again. We're going to slow it down for a minute. If we don't get through lesson 7 today, that's okay. It's not the end of the world. We're going to use the same practice question. Find the point of intersection of these two equations, and then solve the system of equations graphically. What I really wanted to get at was to show the different ways to find point of intersection, which is why I had such a vague graph on the board. And I wanted to show that there are two ways to do it. If you have a vague graph, that you can solve it not just by graphing, but also by completing a table of values. Sometimes what you will be asked in your coursework is to create a table of values, and it will often say from -2 to +2. It'll be something along the lines of, can you graph using the values of -2 to +2? So what it's asking is for you to essentially substitute and solve for the equation. Our first equation is y equals 2x plus 3. Yes, there was a way that we could just graph it, but the other way to do it is through a table of values. So I could use my slope and my y-intercept. So I'll do that for my first one, but this time I'm going to use, instead of going up by singles, I'm going to go up by doubles so that I can fit it all in. So if you're following along on my Zoom slide, I'm on my Cartesian plane. My y-axis, I'm jumping my squares. Instead of making them singular, 1, 2, 3, 4, 5, I would run out of room. I'm going to say that the first line is 2, then 4, 6, 8, 10, 12, 14, 16. So now when I'm plotting, and I'm going to use red, when I'm plotting my y-intercept, it's at 3, and I'm going up 2 over 1. And I can do that because I know that my slope is 2 over 1, and my b, my y-intercept, is 3. So I'm going to go up 2. Now, I am going to keep my x-axis singular, so I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9. That part can stay the same. It's just my y-axis then I'm going to double up on. So I'm going up 1, 2, over 1, up 1, 2, over 1. Here we go. So this is going to make it a little bit more accurate when we try to find our point of intersection. And then, of course, what I want to do is I want to connect those dots. I'm going to connect those dots using a ruler and make that straight line. Now, I'm going to show you how to do it by substituting it into a table of values. What we do is we have our x and our y, and we're going to use the equation y equals 2x plus 3. This time I'm going to say, what if my x was a negative 2? What if it was a negative 1? What if it was a 0, a 1, a 2, a 3? We're going to substitute our x for the values that we've highlighted. So in our equation, y equals 2. Instead of x, I'm going to say that my x is negative 2 plus 3. So now I have y equals 2 times negative 2, which is negative 4 plus 3 gives me y equals, and then here I have negative 1. Substitute x for negative 1. So now we're saying 2 times negative 1 plus 3, y equals negative 2 plus 3, y equals positive 1. What if my x is a 0? 2 times 0 plus 3. 0 plus 3, y equals 3. I'm going to keep going. Y equals 2 times, if my x is a positive 1, that's going to be 2 plus 3. Y is going to equal 5. And I'm going to keep going. What if my x was a positive 2? 4 plus 3, y equals 7. And lastly, what if my x is a 3? 2 times 3 is 6 plus 3, y equals 9. So then if I'm making my coordinate pairs, the x and the y, I'm coming up with negative 2 and negative 1. And then it's negative 1 and positive 1. Then it would be 0 and positive 3. My x I said was 1. My y I solved is 5. Then it's 2 and 7. And lastly, 3 and 9. So what I could do is I could plot those. I could say my x is negative 2 and my y is negative 1. Except I'm going to be doing the exact same on my x and y axis. So that means that I need to be doing negative 2, negative 4, negative 6, negative 8. So if I have negative 2 and 1, it would be here. Then I have negative 1 and positive 1 would be here. And then you can see then I have 0 and 3, which I've already plotted. I have 1 and 5, which I already plotted based on my rise over run. So see how it matches? This is a way to check your work too, to make sure that you're right. So there we go. You can solve that way. Now, if I do my second equation as green, I can do the same thing. Now I can say, let's put it in as a table of values. If x were negative 2, negative 1, 0, 1, 2, and 3, what would my y be? Well, if y is x plus 9, instead of saying x, I'm going to say negative 2 plus 9. Then I get negative 2 plus 9 is 7. I'm plugging it in to y equals x plus 9. Instead of saying x, I'm going to say y equals negative 1 plus 9. That gives me 8? What if x equals 0? 0 plus 9 is 9. What if x is 1? 1 plus 9 is 10. If x equals 2, 2 plus 9 is 11. Which means my last one, 3 plus 9 is 12. So my coordinate pairs would now be -2 and 7. It would be -1 and 8, 0 and 9, 1 and 10, 2 and 11, 3 and 12. So now I can plot those. I have coordinate pairs that I can actually plot. So starting at -2 on my x-axis and going up to 7, there would be my first plotted pair. -1 and 8, 0 and 9, 1 and 10, 2 and 11. Oh, I did that. Okay, that's supposed to be a 12. That's supposed to be 14, 16, 18. So now this one here is an 11 and 2. 2 and 11, 3 and 12. And so I could keep going based on my rise over run. If I am going up 1 and over 1, I'm going up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1. You can see we just had an overlap. So our point of intersection is where they cross, which is at 6 and 15. Here we have, 6 and 15 is our point of intersection, because that is where our two equations, our two lines cross. It's where they meet. So if we were to extend our table of values, if we were to keep going all the way to, instead of stopping at +3, if we went to 6, we would have seen that they both line up at 6 and 15. So two ways to do it: by either finding your rise over run or by plugging in a table of values. You can find your point of intersection. Thanks for that sidebar, team. I hope that makes a little bit more sense. We are going to now continue, I promise, with Lesson 7, Part 2, looking at the quadratic functions and how they differ from linear. So let's get back to our first example of our table of values, finding second differences. We want to find our set of second differences to show if we need to go that far or if it can be solved by first differences. So here we have our example that says, which models represent quadratic relations? Remember, if we're asked to justify our answer, we have to give an explanation. So here we have a column H and P. When H is 0, P is 250. When H is 1, P is 238. When H is 2, P is 48. When H is 3, P is 72. Just like first differences, you're looking at the difference between the set of values. What is 238 minus 250? We're left with a -12. Looking at the second set, what is 202? That's weird. The values don't line up. How come this one says this should be 202? This should be 142. There we go. 202 minus 238 gives us -36. 142 minus 202 gives us negative 60. These are our first differences. They are not equal, so we know right away that this is non-linear. But does it mean it's quadratic? We don't know that until we look for our second differences. So now second differences, we're taking the difference between negative 36 minus negative 12. Remember when you have that negative and a negative together, it's actually saying negative 36 plus 12. So negative 36 plus 12 equals negative 24. And then our second is negative 60 minus negative 36. That means negative 60 plus 36. Negative 60 plus 36 is negative 24. So now our second differences are equal. If our second differences are equal, that means that it is quadratic. What about our second example, our second model? Let's see if our second model is linear or quadratic. Finding the differences between our sets of values, 48 minus 32 equals 16. We have 72 minus 48. 72 minus 48 is 24. And then 108 minus 72 equals 36. All right, so first differences are not the same, so we know it's non-linear, but is it quadratic? Let's take a look at our second differences. We want to find out what is 24 minus 16. That gives us 8. And then what is 36 minus 24 gives us 12. So second differences are not equal, so it's not quadratic. It's also not linear. But today we are just looking at, is it quadratic or is it linear? When the second differences are equal, it is quadratic. If you'll remember, when we are looking at a graph, if it's a straight line, then it is linear. On the board in front of me, I have two examples. First example has height on our y-axis, time on our x-axis. The second example also is comparing height and time. So height on the y-axis, time on the x-axis. The first graph shows this upside down U. We have it goes up in height and then comes down. As if you're throwing a ball into the air, it goes up high, 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 and then after a certain time it starts to fall back to the ground because of gravity. The other example is as time increases, so does height. Anything that goes up must come down. But if we are saying a balloon is rising into the air, and so you're only timing after 15 seconds. After 15 seconds, when you throw a baseball, it's going to go up into the air and then come back down. But a balloon, a helium balloon, after 15 seconds, it's still just rising. It's going up, 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 up. So our first example has this curve. Remember, if it's curved like a parabola, it means quadratic. And if it's a straight line, that means linear. So our first example with the parabola, it's a curve. We can know right away by looking at a graph that it's quadratic. If it's a straight line, you can tell that it is linear. The last example is to look at equations. So remember, there's a table of values, there's graphic, and there's algebraic. And so when we have our equation, we can tell whether or not it is quadratic. With linear, it had to be y equals mx plus b. But with quadratic, we want it to say, you want to rewrite it into the form of y equals ax squared. Ooh, ooh. My board is going crazy. It has a mind of its own. What happened? Why did we go back all the way to the beginning? Quadratic functions. Here we are. Let's try that one more time. Okay, when it says y equals ax squared plus bx plus c, this equation can let us know if it is quadratic or not. Just like with our mx plus b, if there's not necessarily a number in front of the x, it's okay. It can still mean that there's that imaginary 1 there. It can still be in the format. Just because there aren't 3 pieces to this equation doesn't mean that it is not quadratic. Here, what it can mean is we have 1, if we get the y equals x squared plus 7, it can be like saying y equals that imaginary 1 x squared plus, maybe there are 0 x's because we don't see that, just normal x, and that c is the 7. So instead of saying y equals 1x squared plus 0x plus 7, you just say y equals x squared plus 7. But it can fit into our formula because we have that x squared. We need that x squared in order for it to match, because it is showing, if we were to do FOIL, if you remember FOIL, which yes, I know, nobody does FOIL anymore. There's now another way to do it. But the principle behind when you multiply an x by an x, you get x squared. That's what's happening here. Now, because there is that x squared, we know that there's a 1 there. If there was no x squared, that would mean that there's 0. And if you remember, you cannot have a cannot equal 0 in our quadratic equation. So because we have y equals 1x squared plus 0x plus 7, since a does not equal 0, the relationship is quadratic because there is a 1x squared there. Now our second example, y equals 3x plus 2, if we were to write it out, it would be saying 1 equals 0, or sorry, y equals 0x squared plus 3x plus 2. We cannot have a equals 0. If a equals 0, then it is not quadratic. So it works in our first example of y equals x squared plus 7 because a is equal to 1. But it doesn't work for our second example of y equals 3x plus 2 because we're saying that there's 0 as an a for our x squared, and that is not allowed. There is no x squared, therefore the relationship is not quadratic. There's no x squared in the term, so it cannot be quadratic. When we are looking at quadratic models, we talked about how our graph needs to have a curve, and this curve is called a parabola. A parabola is a very specific shape. It's this either a U or an upside down U. Either way, it's a parabola. And there are different parts of a parabola. The parabola consists of a y-intercept, which we've been looking at, and two x-intercepts. That means that not only is it going to cross the y-axis, but it has to cross the x-axis 2 times in 2 spots. So that's why it doesn't matter if the parabola opens up, where it's like a U on the top, or if it opens down, where it's like a lowercase n or an upside down U. Either way, it's crossing our x-axis at 2 points. 1, 2, because it's a U. It's got to cross 2 times. Now the middle of your parabola, if you were to take that parabola and you were to fold it right in half, that was not right in half, that's a terrible, let's see if I can gauge a better half. You can fold it right in half, that is your axis of symmetry, and the point of where it starts to turn is your vertex. So parts of a parabola include a y-intercept, 2 x-intercepts, a vertex, and your axis of symmetry. And that axis of symmetry, again, is if we were to take that paper, fold it, it would be where that fold line is. It's right in the center. Lesson 7, page 11, talks about the opening of a parabola. We want to use the formula y equals a. In brackets, we have x minus h, and then you close the brackets, and that's to the power of 2 plus k. When the equation of a parabola has the a value, that very first number, that's our a, when it's positive, that's automatically telling us that the parabola is going to open up and look like a U. When the a value is negative, that means our parabola is opening down. You can tell the shape of a parabola, which way it opens, which way it shifts, where it's sitting on our Cartesian plane, solely from the equation y equals a times, in our brackets, x minus h, close the bracket, to the power of 2 plus k. A tells us up or down. All right? Here we have y equals 3 times x minus 5 to the power of 2 plus 7. The value of a, so if we were to write it as y equals a x h squared plus, just like in our formula, plus k. The a value here is 3. Because it's a 3, it's a positive. There's no plus sign in front. If there's no plus sign, then it is positive. You can either put the positive sign or nothing and it means positive, but if you put a negative sign, it means negative. So the 3 is positive, that means our parabola is opening up. In the example, y equals negative 4 times x minus 2 to the power of 2 plus 6, the a times x minus h squared plus k, the a is negative. So that means our parabola is going to open down. Now, what happens if there's nothing in front of the brackets? If there's nothing in front of the brackets, we can still put in y equals a times x minus h to the power of 2 plus k. If there's nothing in front of the brackets, it's implied that there's that imaginary one. That imaginary one is there and that it's positive. So then, if we were to put it into an equation, if we said y equals, And then all we have is in brackets x minus 5, close your bracket, to the power of 2 plus 3. It's saying that there's an imaginary 1 there, so this equation would be a parabola that opens up. That's how we can tell if a parabola is opening up or down from the a value. Now, when an equation of a parabola is in vertex form, that is y equals a, and then in our brackets we're multiplying, we have x minus h, and we're closing the bracket to the power of 2 plus k. The values of h and k become the coordinates for the vertex. Remember, our coordinates are the x and y, and it tells us where to plot on the graph. When it's in vertex form, the values of h and k become the coordinates for the vertex. So here it says, state the coordinates of the vertex of the parabola given by the following equation. We have y equals negative, and then bracket, x minus 4, close the bracket, to the power of 2 plus 3. So we need to remember h and k are the coordinate values of the vertex. So here, if we were to write it out as y equals a x minus h squared plus k, we can tell the a here is negative, so that means it's going to open down. The h is, if we were to line it up, the h is our negative 4, and the k is our 3. That means that our vertex, therefore, the vertex of the parabola is located at 4 and 3. So if we look at our blank grid here, our Cartesian plane, we have 4 is the x, because you always do x first, so 1, 2, 3, 4, and 1, 2, 3. Our vertex is at 4 and 3. And we know from A it opens down. So what we can't really tell right now is where it crosses on our x-axis, so we don't know if it's a little parabola or if it's a big parabola, because we don't know our x-axis, x-intercepts yet. But we know it opens down, and we know that where the turning point is going to be at 4 and 3. Let's try another one. State the coordinates of the vertex of a parabola given by the following equation. Here we have y equals, in brackets, x plus 5, close the bracket to the power of 2 minus 2. That's telling us that the x and y, our h and our k, are going to be 5 and 2. Now, a little bit different, because since the part of the equation is supposed to be, let's change this here, it's supposed to be, I'm going to try to write this a little bit bigger so it lines up and matches, y equals a x minus h, and then plus k. When we have the h as +5 and the k as -2, since the equation is supposed to be x minus h, then h is a negative value. When you have a positive and a negative, remember you always get a negative. To make it x plus 5, h has to be -5. Because when you have a positive and a negative, you get a negative. So the vertex, because our k is standing alone, it is allowed to remain a positive, but because our h is in the brackets, our vertex is going to be -5 and -2. So when we look on our Cartesian plane, we have -5 on the x-axis and -2. So our vertex is going to be in that bottom left quadrant. That is all the time that we have for today. We will continue Lesson 7 on Monday. Remember, there is no class being broadcast tomorrow. However, if you are in Cat Lake, feel free to drop by the Learning Center and visit Jillian and Margaret, who will be in community helping with registrations and homework help if need be. I hope